Okay, so I'm going to talk about a few string problems, and we'll start with problems that are relatively straightforward in that we're only looking at the number of characters, the number of different characters that you see. So we're not interested in the exact order of the letters, but just how many of each type of letters it is. So we'll start with first on our first slide. We'll talk about the anagram problem. So what is an anagram? If two strings are anagrams of each other, if you can rearrange the letters of one string to form the other string. In other words, the two strings are permutations of each other in terms of the letters. Okay, so here we have dormitory and a dirty room. Turns out that the two of them are anagrams of each letter. So you can see D is here. There are two O's that are shuffled to be here. There are two R's that are shuffled this way. The Y, the I, the M, and the T. Okay, and so you can see these two words are anagrams of each other. So if you're given two words, how do you know if they are anagrams of each other? Now, the first thing you can try, I suppose, is to try all permutations and see if one of them match. Permutes the first word, first string in all possible ways, but that's very inefficient. In fact, all you have to do is realize that if two strings are anagrams of each other, they must have the same number of each type of letter. So for example, both would have two D's, okay? Both would have one I, one M, two O, two R, one T, and one Y. Both of them have exactly the same count of each characters, and this is a way to tell that they are the same, they are anagrams of each other. So in fact, you can of course do this count in linear time for each string, compare the character. An even simpler way is to just sort the strings alphabetically. Okay, so sort the string, and so this will come out to be sorted B, I, M, O, O, R, R, T, Y. And the second one will come out exactly the same. In fact, when you sort a string, two strings that are anagrams of each other, they will come out exactly the same. So, with this idea, if you ever have a list of strings, so instead of just two strings and ask whether they're anagrams of each other, but you're given a list of strings and you want to know which strings are anagrams of each other. In fact, you can have multiple strings that are all anagrams of each other. What you can do is you can simply sort, and I will call this a signature. So for each string in your dictionary, in your list, sort, and every single string that are anagrams of each other will have the same signature. So if you have a map where the first component is the signature, and the second component might be a vector of string, you can use that, basically this map, to collect all of the strings that have the same signature. So for example, we can write, if this is M, we can write M bracket, you have some function that compute the signature of S, and you just push back S. And for every string that you see in your dictionary, you just do this. Signature basically sorts the string, and this will collect in each entry in the map all the strings that are anagrams of each other. Okay, so anagram is one problem that you can easily do just by counting how many letters of each kind you have. And another way to count is actually just sorting. Okay. Now, a second problem that can be done by sorting is the Canoes not Unix problem. So let me quickly load up the problem here. So here's the problem. You have a number of rules. So for example, the letter G is expanded to GNUS. The letter N is expanded NOT. U is expanded to UNIX. And we start with some string, GNU. And in this first step, every single G in your string would be replaced by GNUS. Every single N would be replaced by NOT. Every U will be replaced by Unix. And then you can do this multiple times. Step 2, step 3, and as you go, the strings, of course, get longer and longer. And in this problem, let me maybe just jump to the sample input. You're given a certain number of such rules, and you're told what is the first letter, what is the initial string, what letter do you care about, so in this case, lowercase t, and the number of times you go do this expansion. And what you're supposed to say is that after expanding 3 times, the number of t's is 6. There's 6 t's. So you go back here, you can see after 3 steps, you have this long string, and there are supposedly 6 t's. Okay? Now, how many times do you have to worry about applying this transformation to? It says that, let's see here. Each of the queries will be written in X and N is up to 10,000. Okay? So you cannot do up to 10,000 steps. Now, the important thing is you actually don't care about the actual string. You only care about the number of times each letter appears. Okay, so what are we going to do? We're going to represent the number of different types of different characters, whether it's A, B, C, up to, let's say, Z. I know that in this problem you actually have more than just A to Z, but we'll just pretend for now that they're only A to Z. And the initial vector, this would just count the number of A's and B's and C's and so on in your initial string. You actually don't care at all what order they come in. So if the initial string is A, B, C, then I would put 2, 1, and 0 here, and then 0 for everything else. Okay. Now, I'm going to make use of matrix operations to indicate how one step of the transformation will work. So let's make it simple, and let's just say that I only have A, B, and C. So I'm not going to have anything more than 3 letters. But if you have more than 3 letters, it's the same idea. So A, B, and C, and let's say you have 2 A's, 1 B, and 1 C. What kind of rules do you have? Let's imagine that you have a rule that says A becomes A, B, B, C, A, like this. So what you can see is that every time you have 1 A in the original string, you're going to end up with 2 A's, 2 B's, and 1 C, right? So another way you can think about it is, in terms of the A, B, and C's in the new string, after one step, how many A's are you going to get? Well, each of the original A in the old one will give rise to 2 more A. So I'm going to write 2 here because 2 times 2, it's 4. Okay, now of course you can also get A by expanding B if there's another rule like that, so this is not the final answer yet. Similarly, every time you see an A, you get 2 B's out of it. So write a 2 here and a 1 to say that every time I see an A, I will get 1 C. Okay, so if this is the only rule, then the matrix looks like this. And if you multiply the matrix, you will get 4, 2, and 1. Okay? And that means if you started with 2 A's, you will get 2 A's, 1 B, and 1 C. The B and C doesn't expand to anything. Okay, they kind of disappear for now. Okay, we have to change that later. And then each A gives rise to 2 more A's, 2 more B's, and 1 C. Now, if there are no rules for B and C, then actually you shouldn't put zeros everywhere because they don't disappear, but rather you should have this. So this is actually 3 and 2. Okay, so whatever, if you started with A, 2A, 1B, and 1C, the 2 A's get expanded by the rule, and the B and C doesn't actually go anywhere. Now, let's imagine that instead of this, you have instead of just this rule, you have one more rule, just one more rule, that says B goes to AC. Okay, in that case, every time we see a B, it's going to go to A and C. So A and C, you need for the equations A and C, so to figure out how many C's you have to look in the new string, you have to look at the row that corresponds to C, so the third row. And then the second column, that's how much a B contributes. So each B contributes 1 C, each A contributes, each B contributes 1 A as well, so that's why we have the 1 and 1 here. The B disappears, it doesn't contribute to B anymore. And then finally you have, if you don't have a rule for C, then it's the same as saying that there's a rule that replaces C by C itself. And then, if you want to know, with these set of rules, what is the number of A, B, and C's after one operation, you do the matrix multiplication. And if I haven't messed up, it should be like this: 5 A's, 4 B's, and 4 C's. And that's what happens after you do one single replacement, one step in the problem. What if you want to do 2 steps? Well, you just square the matrix. If you want to do n steps, you can do the same thing. You just repeatedly apply n times. And when we talked about how to compare Fibonacci numbers quickly, we talked about this technique of exponentiation matrix. This is the same trick here. If you want, you can exponentiate a matrix using the fact that if n is even, you can just square the matrix and then raise it to n over 2. Or if it's odd, then you break up one piece, so it becomes, instead of a times a raised to the power of n, becomes a times a to the power of n minus 1, and n minus 1 is even, and then you can do the same trick. So for this problem, all you have to do is figure out the matrix using the rules, right? Each rule basically will tell you something about a particular column, right? So this rule A, because it starts from A, it fills in the matrix of the column, the first column that corresponds to A. This rule applies to the second column, and this rule applies to the third column. Then you raise the matrix to the power n, and then you multiply by the vector that contains the counts for the initial string. So that's how another problem that you can solve using frequency counts.